use. So I'm going to show you some things that not a lot of other people have seen. That includes a lot of things that are good and some things that are quite bad and ugly to go with them also. So let's get started and do it this way. What we're about is kinetic hydropower, using the power in flowing water, not conventional power from hydropower, using the potential energy from a head differential, which is very efficient, very effective, and very often environmentally damaging. And except for repowerings of dams in the United States, you may be aware that in Vermont we're taking out a lot of dams, and even though there will be a net, probably an increase in power due to repowering, there will be fewer dams, and in terms of the future, much less in the way of dam construction and potentially powered hydropower. Some of the benefits are obvious that I think you're all well aware of, that it's sustainable energy and much cleaner in terms of emissions and certainly carbon dioxide. And as I know from seeing resumes of recent graduates, people are interested in the job creation potential in this field. This happens to be a site we're working on. I'll show you later on the St. Lawrence River in Cornwall, Ontario. Very, very briefly, without getting into a lot of detail, people here may be well aware that the amount of power in flowing water has to do with the cube of the velocity and is proportional to the area of the flow that you intercept. And the forces generally go as the square of the velocity. All of this obviously has a lot of ramifications in terms of designing practical systems to capture the energy. Other parameters having to do with the resource, very importantly, is the depth, the width, length, and whether it's a man-made, this has to do with environmental regulations, whether it's a man-made water body or a natural water body, and restrictions that affect the flow. This is just purely on the physical level before we get to some of the other factors involved. And in general, the flows can be unidirectional. Rivers, like the picture you just saw, the St. Lawrence there is a regular river, or ocean currents, which are unidirectional. And as we're often involved in, and often this entire field is referred to as tidal, although it really is only one part of it, a major part, bidirectional flows in estuaries, tidal straits, which I will show you a project we're working on, and tidal rivers. This gives you a sense of some of the resource potential. I'm not going to focus on this a lot because I'm much more interested in the hardware. But there is potential out there according to these various studies. These are all very large, very raw potentials in terms of what could be there just in terms of the physics. And we'll talk about some of the other constraints that whittle these kind of numbers down to much smaller numbers. But just to show you North America, this was put together by EPRI. And one thing you can see in the kinetic hydropower area, some consider wave in kinetic hydropower, some deal with it differently, but to compare the potential wave resource with the potential tidal resource, you can see that in general, the wave resource is much, much, much larger. Still, and we're dealing with some of these areas. Still, for a country, the US uses about 4 terawatt hours per year. Some of these potentials are quite significant. Although, to put this in perspective, tidal energy itself, on a continental basis, will be one small piece of the renewable energy picture for the future. But going back into history, people have been thinking about capturing the kinetic energy in flowing water for a very long time, well before there was any such thing as a patent office. But these are some of the fun patents that go back, and I have a sheaf of dozens and dozens of these. When you combine them all together like this, not only are some of them, from a practical point of view, kind of silly, but when you combine them like this, they all look kind of silly. This is mine down in the corner here. So that brings us up almost to the future, to the present day. There are a number of ways to capture the energy in flowing water. Some are generally better than others, and on some the jury is still out when we get to practical machines and actually compare them in terms of a number of performance metrics. But just to give you a sense of the kind of ways you can do it, the device could be rotational. Ours, of course, is a horizontal axis axial flow turbine, which you saw at the leading slide, and you'll see a lot more of. And if you look at the factors of whether it can handle unidirectional, bidirectional, or multidirectional flows, ours yaws in order to handle the flows bidirectionally. The turbine itself is inherently unidirectional the way it's designed, so it yaws to face, in fact, in our case, away from the current. It's a downstream rotor. But you can also have cross-flow turbines. Here's one example, and there are many. This actually has articulated blades, but some have fixed blades like a Darius wind turbine of various shapes and various efficiencies. It could be oriented vertically. This particular one is only vertical, but similar ones can also be oriented horizontally. With the axial flow turbines, you can also have various forms of augmentation, typically ducts. This is a turbine that's located within a duct that effectively gives you a larger capture area for a given size rotor. So if you're concerned about the cost and difficulty of the rotating components, you have some fixed components that you can also worry about the cost and problems associated with those too. Easier to overlook, though, than the problems associated with rotating components. You could already tell my bias. This is what I would call an oscillatory type device. This fin articulates, this actually rotates back and forth, a kind of motion that scares me. So I could consider that oscillatory. There are other kinds that are actually even more organic than this, that just sort of look like an unstable blade of grass that has an energy capture device at the bottom of it, capturing that oscillatory motion. I couldn't find a good picture of that for you yet. Here's what I call a translational one, or these tend to look like Venetian blinds. This one, the blinds just go up and down and drive springs and hydraulic mechanisms and linkages and generators at the top. Others have an entire series of these going around this way, and there are actually some that go around horizontally also. So some general capture devices in the most general sense. If you're actually going to make something, you have to worry about, for a practical device, you have to worry about the capture device or turbine itself. And I'm going to focus mostly on turbines because that's what we do. And you have to also focus on the mounting, and the cabling is critically important, and where that cabling goes, getting the power back on shore. Obviously, there are other ways to deal with the energy that you capture. You could turn it into hydrogen locally on a device if it's large enough, and then have a ship come up and take that hydrogen away, or do all sorts of things. But we're going to focus on just generating electricity at the moment. Another one that's often talked about is hydraulic power, where you could replace this with hydraulic hoses. There are obviously issues associated with that. But once you've designed this whole system, and it has to be a system, you also have to include the deployment and retrieval and operation of these devices. So the ideal perfect turbine that has no practical way to mount it or actually get it out there, put it in the bottom of some kind of water body, or even suspend it from the top of a water body, will be very difficult to make into a practical device that's going to get us some usable energy. We have structural issues to deal with in the underwater environment, and we have obviously water chemistry and biology issues to deal with in the underwater environment. And these pertain only to the devices themselves. We'll talk about some of the environmental issues in a second, but we obviously have to deal with sealing and friction and corrosion and various kinds of fouling from things underwater, both living and non-living, along with all the forces, which you'll see good examples of, I'm afraid to say, a little later on. Then in terms of broader impacts and environmental impacts, you're putting these things in the water, and you're taking up some space, you're moving things around, you're potentially changing the velocity of the ambient water and the pressures in local areas, and potentially even the temperature and heights at various stages of whatever water body you're in. Your device could also leak various kinds of fluids, from oils to other fluids. You can create noise. This is a major concern, and a lesser concern, on the East Coast, although one we're starting to see on the West Coast, is EMF. The impacts could be on, in terms of wildlife. Here's a list of some kinds of wildlife that we've been dealing with. Mostly on the East Coast where we've been, not so much the benthic community yet in the East River, because we mostly have rock there.
What's benthic?
Things living in the bottom. Worms and generally smaller things living in the bottom. On the West Coast, we're about to be dealing with mammals, which is a whole new thing. But we do have a lot of fish and potentially amphibians on the East Coast where we've been so far also. I'll talk about that a little bit. But that's a whole other book. You also have to deal with other interests: navigation, recreation, and social and cultural values. For example, in the St. Lawrence River at Cornwall, we're dealing with some of the First Nations there, the Mohawks in particular, it is very important to take all those factors into account if you want to make a successful project, even on a pilot stage. Obviously, you are aware that the first thing about the device itself is its efficiency. That means every aspect of it has to work: the rotor, the machinery the rotor drives, particularly the generator, load matching depending on what kind of load you're going in. In our case, we've been focused mostly on going into the grid, but obviously you could go into other kinds of loads. And then the other cost factors of manufacturing, the capital cost factor, and then operational cost factors having to do with deployment. And I highlighted this in red because this is often underlooked and extremely expensive and quite different from comparisons with wind, where you can go and maintain, you can climb up the tower and maintain a wind turbine at the kind of periods that you cannot do in the water with sizable turbines, because the deployment costs of mobilizing the boats, the ships, the barges, the tugs can be prohibitive. And so you're in the underwater environment, and there is a premium on long-term reliability. You won't know it from some of the slides I'm about to show you, but it is in fact true. Then, of course, other costs that relate to the entire system of interconnection, if you are going to be grid connected, the proximity of the grid, and how you have to interface it to successfully provide quality electric power, which relates to expansions of the grid, particularly for renewable energy, whether it's wind or kinetic hydro, and of course issues having to do with smart grids later on. I think this is the last thing that has anything that even looks like an equation on it. But for those of you who are interested, you probably already know that the power available in the flow is 1/2 rho AV cubed, based on the area that you're actually capturing. It's simply for a free rotor with no augmenting duct. It's simply the diameter based on the radius of the rotor itself. The mechanical power, if you're just focused on rating the efficiency of the rotor itself, the mechanical power it puts out is omega tau. And we are, I will show you our testing, our dynamometry of actual rotors, looking at the actual mechanical power put out by the rotor before any downstream elements, before any gearbox, before any generator, before any interface into the grid. But we will also have that. And that's what we call the water-to-wire efficiency, which is the actual electricity put into the grid divided by the power available. As many of you know, for an axial flow rotor with no augmentation, the power available out of the rotor is the Betz limit times this as a theoretical maximum, which is about 59%. You will actually probably hear numbers greater than that when people are using augmentation or other things and not really doing the calculations the way they probably ought to be doing it. All of this is an area like the early wind industry before standards were adopted, but things are moving much faster, and we already have a technical committee under the IEC, which I serve on, that will be formulating, is the process of formulating standards for kinetic hydroturbines and wave devices similar to the standards for international standards for wind turbines. So people will get it together as to how they calculate these things, how they actually measure these things. Here's some early work that we did at New York University. There, beginning around 80, 81, we started looking at all those possible devices that might capture power from the flowing water. We had support from the New York Power Authority, and ultimately the Department of Energy joined in before it was essentially eliminated from hydropower, and Con Edison, the local utility in New York City, before they were deregulated out of generating power. And so we started with some theory and then did some practical economics as to what systems might actually work reasonably well and might actually someday achieve good economics, and focused on the horizontal axis turbine, and went into some blade design based on very straightforward blade element theory that has been far outstripped by the computer codes that are used today, and designed a series of model rotors at just a little bit below 1 meter diameter level, and did some testing at the Navy, which is what you see here. And this is some of the dynamometry output that we did, showing the angular velocity, or omega, versus, in this case, power, and showing that with a fixed pitch rotor at different water speeds, each of these parabolas represents a different water speed. These are actual data points. You could get quite good power output over variable water speeds with a fixed pitch rotor into almost a fixed load. The slope here of the line shows the slip of an induction generator, which is not intuitively obvious that you could use such a simple rotor and get it over a range of speeds. One of the advantages we have over wind is we do not have a tremendous range of speeds. In the East River, we go from about 0, obviously, because it's tidal, up to about normally 2.1, 2.2 meters per second, maybe 2.5 meters per second exceptionally, and for brief moments over 3 meters per second. Everything below 1 meter per second doesn't matter, because there's very little power in that. So what you're dealing with is a very narrow range. And since we have all the difficulties of operating underwater in that environment as compared to wind, it's always been my belief that we have to capitalize on all our advantages. And one of those advantages is that we have a very narrow speed range, even with the variable resource. We ended up picking out of the rotors we tested a particular rotor design that gave us good efficiency over a broad range of speeds, did not have cavitation problems. You can see we left the tips blunt so that we could get cavitation streams off the tips, and you can see the expansion of the wake from the turbine, which is extracting energy from the flow, and therefore, this is an upstream turbine with a downstream dynamometer. The wake expands because you're extracting energy from the flow, and Bernoulli will tell you that. We got to the point of making a 15-foot diameter. This is a 2-bladed rotor, but the one we chose, this one, is a 3-bladed rotor. And we built a 15-foot diameter turbine for testing in the East River in New York City, which I will show you, which we ended up testing in. That had 2 different insides. One was a dynamometry inside, and one was a generator inside, so a gearbox and generator, so we could do both of those things. And then NYU pulled the plug. The DOE got out of innovative, emerging technology, and eventually got out of hydropower entirely, and it just got back in last year into hydropower research. And so the turbine that we built did not get tested in the East River, but was shipped to be tested under the auspices of the United Nations Energy Project to Pakistan, and that's a long story, but the electronics never got there. And as a result, we never got the data back from Pakistan, although we have videos, very frightening videos of people standing on a flashing turbine barefoot while it was generating power and they couldn't stop it. So we know it works, we just don't quantitatively know how well it worked. So this is the East River in New York City. And this is the United Nations, in fact. This is Roosevelt Island. This is where we're located. This is the famous Queensboro or 59th Street Bridge. This is Queens. This is Manhattan. I won't give you the entire travel log. This is the Roosevelt Island Bridge, and you'll see we're located just north of that bridge. This is called the East Channel. This is called the West Channel. This is where we didn't test that turbine. But Verdant Power, that was created in the year 2000, while I was just leaving the legislature and beginning to work for Bernie Sanders, they started testing a bunch of things, including this ducted dual turbine device up in Canada. And then I joined them in 2003. And to make money in kinetic hydro, we didn't have enough money yet to do our own turbines. But Massachusetts hired us to test this twisted helical, essentially a Darius-type turbine, a cross-flow turbine. This can be used vertically or horizontally. And so we designed a system to load this rotor and did dynamometry on these rotors for the state of Massachusetts. That was in 2004. But at the beginning of Verdant, one of the turbines they had tested, they had read a DOE report from Idaho National Engineering Lab that said that that was in like 1994, that said somebody ought to really follow up on the NYU work. So Verdant did that, and this is before I joined, just. And they made a 10-foot diameter version, basically a copy of our 15-foot diameter turbine at NYU, and tested the rotor and found pretty much the same results. And then that led us to the necessary funding to do our what we call a fourth generation turbine. That previous model there was a third generation turbine. And that led us to being able, with the support of NYSERDA, the New York State Energy Research and Development Authority, and some others, including a lot of capital that was private, which doesn't really exist at the moment, but we hope will come back soon, to do what we call the six-pack, 6 turbines in the East River, in the East Channel, alongside Roosevelt Island, just north of the bridge. With these characteristics, the same 3-blade design. So this design is now a 1982-83 design, still in the current day. And they have passive yaw, they have a downstream rotor. I'll show you a picture in a second of what it looks like. They are essentially rated at 35 kilowatts. 5 of them have generators in them to be grid connected, and one of them is purely a dynamometer. From the outside, they all look the same, which you'll see, and that's basically what the turbine looks like. Now, most presentations from most kinetic hydro developers pretty much end at this point with the SolidWorks model and the retouched photograph showing what it might look like underwater if you could see through the East River, which you can't, because it's so full of biological activity. It's a very healthy river, actually. I need to say that. But this is an actual photograph of the first turbine. And they all look like this, although this is turbine number 1, and this is actually the dynamometer. This was made in upstate New York from parts from all over. So the purpose of the project was firstly to demonstrate the concept, which means doing everything. Building them, designing them, building them, deploying them, getting them to actually generate, seeing how well they yaw, issues, what I call endemic issues having to do with fouling, issues that are really hard to solve. If you have a leak, you can solve that problem. That's just an engineering problem. If you have endemic problems of there are just too many fishing nets flying through the river, or there are too many, there's too much biofouling, those are harder to solve, although the fishing nets are the hardest of all. How well it works connected to the grid, because this essentially has not been done before, and then measure the actual performance, the rotor hydrodynamics, and with the entire turbine system there, not just a pure rotor in a lab, and not a scale model, and the water-to-wire efficiency all the way through to the power line. Then environmental impacts were a very, very large part of this project. The entire project was about $6 million, of which about $2 million was spent on the turbines and about $2 million was spent on environmental monitoring, to give you a sense of the scale there. And most of that had to do with fish, and I'll show you a little bit of what we did about that. As I say, that's an entirely other book. So here we have a multi-turbine array. This is a first. We're looking at different array spacings. As you know, the turbines may interact with each other. As wind turbines interact with each other, they create wakes. That's an area of lowered velocity in general and changed turbulence in specific. Then we had some rotor issues, and so we made new rotors, and that's a part of it. And then testing turbine longevity is also extremely important. Very, very important. So again, here's the site to situate you a little bit. Here's the East River split by Roosevelt Island into two channels. This is basically a giant rock in the middle of the river. The flow here is fast enough that there's essentially nothing but bedrock on the bottom. There are some very large, like meter scale boulders that affect the flow to some degree. The East Channel is, there's a little bit of shoaling on this side. You can see where the bridge piers are relative to the shore. This is the deeper part of the East Channel. The West Channel is the main navigational channel, and therefore until 9/11 we would have been totally free to use the East Channel. Since 9/11, the West Channel is closed whenever the UN is meeting, particularly when the President of the United States is there, so that no ships can get anywhere near the UN. There is an exclusion zone there anyway, but for safety's sake, they close the West Channel, which means more shipping goes through the East Channel, although certainly not large ships. They were going to weld this bridge down. It was almost non-functional, and now they have a multi-million-dollar restoration job that's underway to make it lift and whenever the traffic needs to go through. So we no longer have the whole channel to ourselves. That's obviously one of the issues you need to deal with is navigation. Another one that's very important is community support. And the entire community of Roosevelt Island, as you may imagine, we deal with 24 regulatory agencies, many of which require, and we would have them anyway, public hearings and public meetings. And when we hold public meetings here on the island, you've never seen a community come out and say, please approve this as fast as you possibly can because we want renewable energy on our island. Our office is in this new building, the Octagon building, which is built around one of the most famous insane asylums in the world, and actually faces the other channel. And so that community support has been terrific. Just to situate you a little bit, the East River comes up here and then heads east into the western end of Long Island Sound, which is out here, past LaGuardia Airport, Rikers Island, famous prison, and some other terrific landmarks. This is the Harlem River that flows over and connects to the Hudson River, or the North River, over in this area. There's very little net flow, actually, through the Harlem River. So basically we have a pure tidal strait here between New York Harbor and Long Island Sound, two very large bodies of water that make the ebb and the flood here almost equal, which is a very nice situation to test in. The flood's a tiny bit stronger. You can't see this, so I won't focus on it. This is our control room for the project, and this just schematically shows you the 6 turbines. These have a 6 diameter longitudinal spacing between the 3 rows. They have a halfway offset. They have 2D between the turbines crosswise, and they're offset from the middle row to the end rows. And these show you some of the hydroacoustics we use to monitor fish far field and near field around every pair of turbines from the riverbank at 3 levels, look with split beam transducers that look across the river 24 hours a day, storing many terabytes of data on every fish that passes through the East River anywhere near any of our turbines. So that is another first in the world kind of array of hydroacoustics. And then one high-frequency multi-sensor array that can actually give you basically 2-dimensional movies of what's going on with the fish, but has a much shorter range. Can only see this nearby turbine. Our control room is in a shipping container, and so we have all the computers for the split beam transducers. We have a corner of it is devoted to the dynamometry on turbine number 1, which includes an air brake that we can variably load from no load to stall at different water velocities. We measure the water velocity with an ADCP, which is located in this area, an acoustic Doppler current profiler, which is critical, and we need more of them, as you'll see. And then the generators from the other 5 turbines, 3 of them go to a load which is the nearby supermarket, and 2 of them go to a load which is the local parking garage. They're run by the Island Authority. And they go to those loads on the customer side of the meter because we got the first ever waiver from FERC, the Federal Energy Regulatory Commission, to put hydropower in with not a full license, which is a multi-million-dollar effort just to get a license, because they're designed multi-megawatt dams and last 50 years. And we got the first ever waiver called the Verdant Power decision to allow us to do this if we connected to the customer side of the meter, so we didn't actually feed back into the Con Edison network, because that would have violated the Federal Power Act, which was written now 70 years ago. And we also had to promise that we would actually reimburse Con Edison for any power that we offset from their customers. But we had to agree to that, but they didn't actually, they haven't called us on that yet. This is a satellite photo of the site. Here's the RIOC garage. Here's our control room. And here's the bridge to situate you. And here are the locations of the 6 turbines. We have buoys to keep, we have an exclusion zone and signs to keep ships out of this area, which has actually been very successful, except having to retrieve the buoys when they break away. And 2 ADCP locations right on the edge, which had to be inside the exclusion zone, which is a real problem, because these really need to be outside, upstream of the turbines on both the flood and the ebb. In this case, the flood is in the more northerly direction, and the ebb is in the southerly direction. And these rectangles indicate 4 of the 8 locations of the frames that you'll see that hold the transducers that give us the fish images shooting across the river at 3 different levels on both sides of each pair of turbines. And this is the far field south. There's also a far field north. This shows the ADCP and its mount sitting on the river bottom. I don't know if you're familiar with ADCPs, but it's a way to measure flow in a river like this. It gives you a good mean flow. We're going to have to be doing more, which I'll mention in a second, about getting more detailed small area flow in order to get the turbulence intensity. But we can break this down into different bins and get the full velocity for each bin simultaneously, and then we do a weighted average to give the effective velocity at hub height. obviously, if you're going to do efficiency, measuring the velocity is very important. And you'll see what those signals look like. It's a little bit bright in here. It's a little bit hard for you to see this. I wonder if we can we make it a little dimmer? Oh, yes. Good. These are the frames that hold the split beam transducers that shoot across the river. This location here is our staging area at the Ravenswood power plant, which is just across the river and a little bit south of our location, which is behind that bridge pier. You can't quite see it. These actually sit on the edge of the river in this orientation and shoot across with 3 beams at different heights to see what's going on with the fish. And this shows you what those beams do. The green beams from the split beam transducers. The images on the right here these colored beams are different angles from the beam of the multi-sensor array that can actually give you very nice video of fish that are in the area in question. You'll see that this is meters out from the sensor, and here's a fish. This fish is about 1 meter long, or the better part of 1 meter long, about 13 meters out. The turbines are about 18 meters out, and what we have found overwhelmingly is that fish don't go there. They like to stay, and here's a school of small fish, and these are really, you get really beautiful moving images of these things. They like, and these are even closer in, they like to stay much closer to the shore. That would make sense if they're trying to conserve their energy with these very fast currents. There are maybe exceptions to that when there are striped bass runs in the spring and in the fall that pass a lot of fish through this area, and but we have seen very, very few fish in the area where the turbines are actually located. Getting back to the turbines, these were the first 2 turbines, and as I say, turbine number 1 was a dynamometer. It had a air brake that we could control, a lot of instrumentation, temperatures, leak detectors, torque sensor, tachometer, everything you would need to do the dynamometry, and also things related to the preservation of the turbine itself, all with digital signals sent back to the control room where we could monitor it. Turbine number 2 was a generator type turbine which had here's the same bearing housing that holds the main shaft, a coupling, low speed coupling, gearbox, planetary gearbox, similar to what's used in wind turbines and many other devices, and induction generator directly connected to the grid. Mounting and installation. This is a one-of-a-kind installation where we put piles in the river bottom. And each turbine is mounted on its own monopile, and these were drilled into the bottom, grouted in. That's what this huge concrete pumper is doing. This is a jack-up barge. All of this is extremely expensive, extremely time-consuming. The river bottom, the rock is weathered, and the top part of it is different in every location. Some places these had to be only 12 feet deep. Some places they were 24 feet deep. Very expensive, very effective, never to be done again. Involved a lot of diver time, profoundly to be avoided if possible, because it's dangerous work, but these guys were unbelievable. They never did anything wrong, which says something about the coordination of the design of the elements that they had to deal with underwater, but also their unbelievable skill and resourcefulness. And they even had wrenches not work, but they would make things happen, and they only have during the slack period, depending on the actual time of the lunar month, between 45 minutes and an hour and a half to do their work and get out before they become seriously imperiled. And we came close once out of many, many dives to an accident, but there were no accidents. Here's another view of the deployment. This is actually a later deployment, but it's a cool photograph, so I wanted to include this too. This was later in the process when we had taken turbines out, and you'll see we had changed the rotors and put them right back in without any servicing. But this is the actual first deployment of turbine number 1. This is a cheaper barge, a jack-up barge that has 2 spuds. It drops down. It doesn't pull itself up out of the water. This is the output from the dynamometer. This is just the front end of the computer display that shows the kind of data that we're getting, various temperatures from the air in the nacelle itself, bearings, water flow in and out of the brake, which was water cooled. You'll see, we were actually getting a lot of power out of it. Here at this moment we're doing 36 kilowatts. These were rated at 35 kilowatts, which turned out, you'll see, it was a pretty good rating for the actual speeds we got. We did get electrical powers out momentarily over 70 kilowatts because of the nature of the flow. You'll see in a second. So here's data from the ADCP is coming in here. This is the weighted average hub height velocity, the direction. And down here you see a little history. Obviously this is not what we used for data processing. We stored all the data. And it's very important that these were always green. Because when they're not, that means that we're leaking. And we also even looked at the humidity inside the nacelle, which was really excellent right up until the end. Very, very quickly, this is the kind of thing we did with the dynamometer. Because you have no control over the water velocity and it's constantly changing, it could change 20% in a couple of seconds. Very, very chaotic, variable input, which you'll see better in a second actually. This is water speed, but this is a very smooth signal, the blue here. So what you need to get meaningful data of what the rotor is doing or wants to do ideally at every water velocity is to collect huge amounts of data, split it up into narrow water velocity bins, take all your torque and rotation speed data from that, and just like you saw before, plot all that data at a given water speed and see what you get in terms of performance. So what we would do is load the turbine. You see the black line here is the torque. We would apply air pressure to the brake. This could be done manually, and this could be done automatically. As you go up, the power goes up. That's the red. The rotation rate goes down until you stall it, and then you do it all over again. So you can see what's going on. And you just collect this data over and over and over again until you have a tremendous amount of data which you can average. Then you bin it, and then here we have torque versus rotation rate. Here you have power versus rotation rate. This should be a linear fit. This should be a parabolic fit. You see there's a tremendous amount of noise in the data, which is why you need a lot of data. But if you take the peak power point from each one of these water velocity slices and you plot them, power as a function of velocity, the peak here would be perfect load matching that you're actually extracting at that point. Then they hold together quite well, and this is, I forget how many thousands of data points are here, but many, many data points. So this is the actual performance of the turbine. There's another way of viewing that. Each of the blue ones are these particular water velocities. The red ones are all the other water velocities, and these show the peak power points and the operating curve for the turbine. Now the turbine would tend to start to rotate about 0.8 meters per second, and the most that we got a reasonable amount of data for was 2.2 meters per second. So this was the area in which we were operating. And because the velocity goes as the cube, in terms of annual kilowatt hours produced, the amount below a meter per second is not all that important. But here is the dynamometry result of the efficiency of the rotor itself, or the coefficient of performance, as a function of water velocity. And between 1 meter per second and 2.2 meters per second, it goes from about 52% efficient to 41% efficient out of a theoretical maximum of 59%. So we're very happy with these kind of results. This shows what the electrical generator turbines are doing. These are the boxes, the controller boxes for each turbine that go right into the grid. These have protective relaying and also
extremely simple logic that turns the turbine on and off depending on whether it's able to generate power. There's a display for each turbine and generating power. This is the first ever multi-turbine into the grid power generation. This is a typical generation cycle. The red is the water velocity. The black is the water velocity smoothed a bit. You can see the water velocity starts to come up. The turbine starts to turn, starts to speed up. We get to a certain point, and then it locks into generating at a fixed speed. It's an induction generator connected directly to the grid. Generates over the entire period of time, and then when the power gets too low, it trips out, speeds up briefly, and then slows down as the water speed goes to 0. Over that period, and we would take these periods, they're all different depending on what's actually going on with the tides. They have different lengths. So we would normalize the generation time from 0 to 100%, and then plot the water speed and the power output and the effective water-to-wire efficiency, which was typically in the range of 30 to 40% water-to-wire for the vast portion of the tidal cycle. And how you actually, and we would divide it into quintiles and average the efficiency over different quintiles. And how you do this will be part of some of the standard setting that we're going to be talking about in terms of comparing different devices. But this kind of relatively flat efficiency curve, water to wire, is what we're really interested in. We're extremely pleased with that, and we have a plot like this for hundreds and hundreds of tides. This just shows the water speed distribution, and this is the power distribution of turbine number 2. We got a mean power of about 14.5 kilowatts during generation. This doesn't include the time between tides that it's not generating, and that's considerably higher than what we had hoped for, and different power levels. You can't read this, but different power levels for different percentages of the time. I'm already taking too much time, but these show for 5 different generator turbines the actual efficiency plotted when the turbines were operating freely and not interacted with by other turbines. And each of the 5 turbines performed as it was supposed to when it was able to do that. So basically these were the results. Multi-turbine, the field directly connected to the grid. Bidirectional operation was proven equally in both directions. The operation was continuous and automatic. The moment the turbines are put in and released, they generate. Even our guesses at some of the setting parameters were right, and we didn't even have to change them. Altogether, the project did over 9,000 turbine hours of operation and did achieve water wire efficiencies over 30%. Some of the other parameters that are resource dependent, and this is very important. People talk about capacity factor a lot because capacity factor is extremely important. If you have a turbine that operates well, regardless of what it is, capacity factor will be determined by the resource itself. In the East River, we were hoping for 27%, which is about what we would get from a sinusoidal kind of tidal current. We have flatter tops than that, so we actually got a better capacity factor. In Puget Sound, we're going to have much lower capacity factors because the tides are mixed, and there's a lot of tide action that's not usable. In the St. Lawrence River, with the continuous river flow, we're looking at capacity factors over 80%. The 5 turbines with generators generated over 80 megawatt hours into the New York City grid, which really is not that much. It's just the beginning. But we did prove that all the aspects of the turbine worked, from hardware to software, and the yawing, which hadn't been done before, was very successful, and the control, and possibly most important of all, because as I say, these are all fixable. We had no fouling from any debris in the river, and this is a very busy, active place with a lot of commercial and activity around it, and that's a very good very good finding to us. That goes to things like protective screens and things like that, which we generally think would cause more trouble than they would solve. I'll go past this very quickly. It's just a summary of the performance of the turbines. And then finally, the lessons learned. We got a lot of experience, and we need more experience. We need better, the advanced acoustic Doppler measurements of the water speed were not what they could have been, and we need better measurements of the turbulence intensity, which is going to take a different kind of instrument that feeds into our new computer modeling. We did have rotor structural failures, which I will go through very quickly and show you. And we learned a lot about array spacing, and we need to learn more about that and do more testing, and we're doing more CFD work on the hydrodynamics of that. We did a huge amount of environmental studies, and the good news is that we think that many of the regulatory agencies are going to allow us to focus that in the future much better on what are more likely to be effects rather than the very, very broad brush approach we took. This just shows you very quickly, I'm going to go through these very quickly because I'm running out of time, some of the loads on the turbine and the basic situation in the water column at the RITE project. This shows you the structure and the testing of the first set of rotors, which go back a very long way in design and had failures. As you can see, this is the dynamometer. The dynamometer can allow the turbine, can not only load it at much higher torques, but can also allow it to rotate freely, which increases the thrust load on the turbine greatly. Although I do think ultimately in the water resource we're going to be able to control that, possibly even without brakes. These turbine blades did fail. Then we went to cast AlMag blades with the same steel hub. We had one failure with that. The generators didn't fail it, but again we were able to fail the blades with the dynamometer. And in particular, the castings that we got from the particular vendor had hydrogen porosity in them and were not up anywhere near up to the material strength they should have had. Let that be a lesson to you all. We also found that the water velocities were considerably higher than all of the months of data we had collected prior to the deployment, really the design and deployment of the project, which argues very strenuously for long-term velocity measurements. The red there is over 2.5 meters per second. And the previous measurement, the peak we ever saw was 2.1. 3 months. Also, they were done from a survey boat, and this data is from an ADCP that sits on the bottom, and it makes a big difference that way. These are the next blades we designed. We finally had FEA. You could see the blades broke here with the area of maximum stress. We designed blades with new thickness tapers. We re-examined the hub and found a weakness in the hub. We redesigned the hub and improved the hub connection and simplified the hub connection to the blade. Also made it much easier for people to assemble and torque up. Started doing significantly more inside and outside, especially outside CFD work to get pressures and loads. And this is what we call the Generation 5, the first Generation 5 turbine, the hub, and the blade that went with it. And this is the blade being tested with our new partner, NREL, at the National Wind Testing Center in Boulder, Colorado. And this is one of their wind turbine blade testing setups. But here we're testing the entire hub and the new blade. These were static tests. These were multiple load static tests done in 2007. And it did extremely well. And we are just beginning to do, we're about to begin to do longer-term fatigue testing on this particular blade, even though we are also working on the next design. We did another deployment of 2 turbines with the new rotors at 12D spacing with no offset on those 2 positions, position 1 and position 5. And these are the new rotor parts. There's the new rotor put together. They went together very quickly, which was nice. Here's the same old beat-up turbine going back in the water with the new rotor. The new rotors performed beautifully. So we changed the shape slightly to make it stronger, more structurally successful, but we didn't want to damage the hydrodynamics, and we proved to ourselves that we didn't. This also shows some interaction of the turbine. Again, this shows that the efficiency of the rotor and the entire generation system was still up to snuff. And this is not a computer model. This is actual data from survey data showing the performance of 4 turbines. This is actually earlier than what I was just showing you. But you can actually see in the velocity, you can see the wakes of the turbines. This is all 3-dimensional data, and this is a slice through the turbine rotor disks. And we're going to be doing more as we are able to deploy more systems, take more real-life data like that also. Then we did a lot of data focusing on turbine interactions. We're able to look at the generation time, the cut-in velocity, that's what some of these are, the generation period. We're able to compare the turbines in many ways. This has to do with the impact of the turbine wakes on the ADCP signal itself. So we developed ways of looking at the water height differential to see if that correlated with the power output of the turbine. It correlated extremely well. This is the blue lines there show the output of the turbines, and the black line shows the prediction, which you can get off the web, of the height differentials for each individual tide. Here we are on the flood, comparing those for the 2 different turbines. Here we are in the ebb. Turbine 5 gets the better flow on the ebb, turbine 6 on the flood, and so they reverse positions on these 2. And then I will go through this very quickly. We show the different powers in both directions as a function of water height. And ultimately, we have turbine 5 data with and without turbine 6. As you can see, on the ebb, where turbine 5 is in the clear, it has essentially no difference between flood and ebb. On the flood, however, where turbine 5 is in the wake of turbine 6, there's a very significant reduction in power. And so even at 12D, 12 diameters downstream, if they're directly in line and not offset, you're going to have a very serious problem with power output. Here's some. This was a mounting failure. Turbine number 1 worked perfectly right up until the mount dropped it on the river bottom. You could see some of the forces involved. One of these radial bolts pulled right through the steel casing that goes around the pile there. This is actually a success story. Inside here is a water-wetted bearing for our yaw, which you can't see in this lighting, but the surface is beautiful. They could have lasted 20 years easily at the kind of wear rates we saw. The carbon ceramic face seals we use as our primary dynamic seal worked beautifully. This is turbine 1. We had an ordinary O-ring static seal fail. I knew this would be your favorite part. Here's one of the here's the graphite part of the carbon ceramic seal taken apart. Mirror finish, there's a tremendous amount of grit. Every open area near these turbines was full of grit, yet the faces were pristine. However, on turbine 3, when it was assembled, one of the O-rings on the carrier was damaged, so it's as if it wasn't even there. And you can see the watermarks inside the other bulkhead for turbine number 3. On turbine number 3, the O-ring there on both ends actually was fine. It was the assembly of the seal O-ring that failed. And you can see the difference here on the shafts. This is the shaft from turbine number 1. This is my actually after a year and a half in the water, still unrusted. This was turbine 3 that had the O-ring seal failure, and the bearings, and of course the shaft and so forth is in bad shape. In fact, the turbine number 1, these are the insides of turbine number 1. This is the brake. You can see it's covered with brake dust. It gives you a sense of how much braking it was doing. And this is where the water cooling hoses and the instrumentation, and these are water detectors, comes out of the turbine. And we expect to put the dynamometer back into service. This is the torque sensor up here. So here are some of the results of the findings on tearing down and inspecting turbines 1 and 3. In June, we expect to take out the other 4 turbines and inspect them. This is where we're going with the design. These are some of the things we're going to combine. We were using off-the-shelf components before, by and large, and now we're doing a design that's custom and much more highly integrated to do exactly what we need to do. And that gives you a sense of that. I can't. And that was actually our first generation 5. This is our second generation 5, where we're using far more in the way of castings, especially this section of the nacelle and the hub. And we're going to a custom gearbox, and we're doing a very significant parts reduction. This is what the inside of that looks like. We're doing an augmented seal and pressure balancing system to make sure we don't have any leaks, because we're going from a 2-year period to a 5-year period of operation without servicing in order to get the economics to work. This is what some of the new blade work looks like, and some of the new mounting work, and we even designed a new mount to hold the ADCPs. And we're working with NREL and Sandia National Labs on a project to work on new, larger composite blades, and we also got the first DOE Advanced Water Power project, now that they're back funding research as of last year, award to work on these larger composite blades and test them. And we're working on a project I'll show you with the Navy to work on deeper systems, different mounts, and different kinds of cabling. I won't spend any time on that. Obviously, there are a lot of factors involved. We've applied to FERC for a build-out of 30 turbines and a 1 megawatt field in this area of the East River, expanding where we have been. That's what that looks like. That would be a 1 megawatt project, still by most comparisons small numbers. And this is the area we're looking at in the St. Lawrence River for Cornwall, Ontario. And this is the area we're looking at in Puget Sound, Admiralty Inlet, in that area for a system there with the Navy, a pilot system of 3 to 6 turbines. And that's where we're going for now. So I will leave it there. Thank you very much. I hope I didn't go too long. And I'd be happy to take any questions, any suggestions. Yes?
I think just a couple of questions in the interest of time.
This may be a silly question, but why the East River and not the Hudson River that is fresh water and unidirectional flow?
Actually, the Hudson River is tidal for 150 miles and is near New York, is saltwater, and has very low flows. The Hudson River is a mixed river. It's part river and part tidal. And as a result, they're very asymmetrical. And the flood is very weak because of the river flow, and the ebb is better. So the flood is virtually unusable. In the East River, it's almost purely a tidal strait, and we get almost equal flows.
I'm kind of curious about economics, just how this may compare, especially with the first year, you're saying how the economics will compare for electricity generation, and then with what you've learned, how much closer, because I assume it's not economically viable right now,
You're right.
but how it'll progress, like how you think what you've learned from here may reduce the cost.
Right. The capital cost, obviously, of these prototypes and small-scale systems is very large. There are other people working on larger systems. You may have heard of MCT in the United Kingdom that has a megawatt-scale system. It's actually 2 turbines, 2 600 kilowatt turbines. all of us are looking at economics similar to the early wind industry where the capital costs were extremely high. But I have every reason to believe the capital costs will come down to reasonable levels. At the 35 kilowatt level, they really have to come down. At the much larger level, you can afford to do different things, possibly variable pitch, possibly upstream rotors, more active controls. But at the 35 kilowatt level, you're really constrained. But in both cases, I don't think the ultimate limiting factor is going to be the capital cost. It's going to be the operating cost, the maintenance, and the cost of deploying, cost of retrieval, extended period of operation underwater is of critical importance. So it has to be very simple, clean, strong devices that don't get fouled. And obviously you have to deal with corrosion and fouling, biofouling also, which has to do with coatings. We used conventional coatings, which was very successful in the East River. We had almost no biofouling at all. And part of that may be due to the speed of the rotor, which turns at 35 RPM. I mean, it's not actually going very fast in terms of most of what we think of, but it may be enough to keep growth off, in addition to the coatings we used. But certainly in Europe, and sooner than later in the US, we're going to be going to non-toxic coatings. There's a lot of research going on in those coatings, and that'll be very important to us as it is to commercial shipping. So there's a lot of driving force there, which is very good.
Okay, I think since we're running a little late, I'll encourage those of you who still have questions to come and to ask them down here later. But let's thank our speaker again.